Okay, today for Unit 5, Lesson 4, Comparing Polynomial Functions. We are going to look at understanding the similarities and differences of different types of polynomial functions, even, odd, and zeros. Okay, so a little bit of a recap from our previous lessons. An odd degree function has at least one x-intercept up to a maximum of n x-intercepts. So if you have a degree 3, right? Your n is a maximum of 3 intercepts, and then n is the degree of the function, okay? An even degree has 0, because remember, you have both your n behaviors the same, which means that you could have it not touch your x-axis, okay? Or you could be pointing down as well, to a maximum of n x-intercepts. So if there's the 4, so then that would be your degree as well, up to 4 x-intercepts. Okay, so here's what we're kind of looking today. So an even function satisfies the property that f of negative x is equal to f of x for all values of x in its domain. Also, it is symmetric about the y-axis, which means it has a line of symmetry. So we're looking at a little bit of symmetry today about the line x equals 0. Okay, an odd function satisfies the property f at negative x is equal to negative f at x for all values of x in its domain. Also, it is rotationally symmetric about the origin, which means it has a point of symmetry about the point 0, 0. That will make more sense as we go through the lesson. Okay. So what we're going to do is just do a little bit of recap on some end behaviors. Okay, so remember, end behaviors for an odd degree polynomial function have opposite end behaviors. So one, if it starts up, an odd degree has to finish pointing down, or if it starts pointing down, it has to finish up. Okay, remember, if the leading coefficient is negative, that means it's going to finish pointing down. Okay, then the function extends from the second quadrant to the fourth quadrant. That is, as x approaches negative infinity, it approaches y approaches positive infinity, and x approaches positive infinity, y approaches negative. So some examples here. So starts pointing up, whatever the example is. So here you have like your blue line starts pointing up to the left, so it has to finish pointing down to the right because of the leading coefficient being negative. That negative means it finishes pointing down to the right, okay? That is for your odd degree, okay? If the leading coefficient is positive, and you were talking about an odd degree polynomial, remember we have opposite end behaviors, but that means we finish pointing up to the right. So you know you're going to start pointing down. Okay, again, regardless, they give you a couple of examples of different functions that could be drawn there. Okay, again, now looking at even degree. If you have a negative coefficient, that means both will point down. That's what that negative means out front. So examples are anything like this with both end behaviors pointing down. And then if you have an even degree polynomial function with both being positive, you're going to have both, that's an arrow, point up. So there is examples of those ones. Okay, so that shouldn't be new to you. That should be a review, but that is a great recap if you wanted to copy that out for kind of like a little note to help you with homework and studying. Okay, some more recap. So some sketching here. So I want you to sketch the functions with the following criteria. So it has to be an odd degree and 1, 0. So an odd degree, remember that you have opposite end behaviors. And I just want you to draw 1, 0, so 1 x-intercept. Honestly, this could have so many different examples, so I'm just going to put an example up on the screen. Here's one that is degree 3 with 1 real 0. There's your x-intercept. And then you know that it's an odd degree because your opposite end behaviors. It could have also gone the opposite way. You could have finished pointing up to the right. It's up to you, okay, as long as you just draw with one x-intercept. So again, there's lots and lots of different examples. That's why it's just sketch a function, okay? And it's just criteria it has to meet. So as long as it meets the material, you'll get the mark, okay? This one's opposite end behaviors. You know opposite end behavior means odd degree. Okay, and you have to have at least 3 zeros, which means that the lowest that our degree could be is 3. Okay, it could be 5 though, it could be 7, it could be whatever you want, but the lowest that it can be is 3. Okay, so opposite end behaviors, here's an example. So they did degree 1, 2, 3, 4, so it would be degree 5 here. Okay, and 3 real zeros, so here's 1, 2, and 3. Again, they just drew that example, but there is lots and lots and lots of examples that you could have sketched that have that criteria, okay? Again, I want a Cortic with no zeros. What does Cortic mean? That means degree 4. Okay, with no zeros, degree 4 can either be both pointing up or both pointing down, depending on what your leading coefficient is. So this example is, we're just going to draw it pointing down. Remember that no zeros means it won't cross that x-axis, okay? And you know it's degree 4 because you have 3 turning points there, okay? And then here's another Cortic with 2 roots or 2 x-intercepts and a turning point at y equals 10. So a little bit more specific here. You are going to want 2 roots and you want it to go through and turn at a value of y equals 10. So that is the point y equals 10. Okay, because it's on your y-axis. So you would have a line here at y equals 10. Okay, so it wants a turning point. So it needs to be Cortic, so it's degree 4. Okay, you know that it's going to have to point down because to have a turning point here and you have to have 2 roots, it's got to point down. If you went the other way and pointed up, you wouldn't ever hit the x-axis. Okay, so if you draw something like this, let's touch our axis here for a turning point. So we'll put a turning point here. Okay, and then, oh, actually no, I'm gonna change this. Sorry. Sorry. Did it drop? No, it only erased that slide. Sorry, I apologize. Okay, so I wanted to erase that. So this one, we're going to go at y equals 10. This was all correct. I changed what I wanted to do. Okay, then you need a turning point at y equals 10, so you know it's going to turn there. Okay, and we only want 2 roots, but we know we want it pointing down. So let's go here, and then a turning point at y equals 10 because it's Cortic and degree 4. That's what erased here. Okay, and you know it's degree 4. You can have 3 turning points there, but you couldn't have 4, or it would be higher than a Cortic. Okay, but there's your 1 0 here and your other 0 there. Okay, again, you could have drawn a couple different ones, but this one wouldn't have as many options because it has degree 4, 2 roots, and a turning point y equals 10 that you have to be able to satisfy. Okay, now looking at what we talked about at the beginning, so we're going to talk about what a little bit of symmetry is. Okay, so symmetry specifically, so for some polynomials, though not many at all, they can be symmetrical about the y-axis or about the origin. So that is your rotational symmetry. Okay, so we're going to look at even functions and odd functions being symmetrical and how we're going to be able to determine that. Okay, so again, there's not very many that are actually symmetrical about the y-axis or about the origin, but we'll show you examples of ones that are and how you figure out if they are or not. Okay, so for even functions, remember our criteria, so this is important, you'll want to write this down. So if you have f at x, so you have your function, you want your negative value, so here's your f at x here, you want your f of negative x, so your negative values, to be symmetrical about the y-axis. Here's your y-axis, so you want everything on the right-hand side, which is your positive f at x, to equal the f at negative x on the left-hand side, okay? So an example, f at x equals x squared is even, because if you are to put 1 squared or negative 1 squared, you are going to get the exact same answers for y, creating that symmetry about the y-axis. Okay, so an example is just a basic parabola, y equals x squared, okay, to give you a even function that is symmetrical. Okay, remember for odd, this is from your first slide, for odd functions, you want your f at negative x to equal negative f at x, okay? So that means a cubed function is an example, a cubic function, okay? Rotational symmetry about the origin. So this is actually, if you were to rotate it about the origin, is going to look like this down here in your third quadrant. So first and third quadrant look the same, but it's rotated. Okay, so you haven't actually totally flipped it like you did with a parabola. You rotated it about the origin. Okay, and this means, so f at negative x, so f at negative x would be down here. These are the values that it gave you. And then if you find f at x but then put a negative in front of them, that is what that means. Okay, so again, I'm going to show you examples of that for that to make a little bit more sense, but this is a good idea to copy down the definition, this example here, and then the graph here, okay? So copy that out. Don't necessarily need to copy this down here, okay? That's an example of rotation about the origin though, okay? If you have something that is neither even nor odd, you can see this example here of why it is not, because this is not on your x-axis, so it's not rotational, definitely not rotational symmetry, okay, about the origin, okay, because you don't have, like, if this is half of it, right, this line down here, it is not symmetrical if you were to like flip it into another origin for half of this. So it's not rotational about the origin, and it is not symmetric over the y-axis because it has been moved. It's moved to the right one. It's moved over 1 unit to the right. So it is not symmetrical, so you can't consider it an odd function or for an even function. Okay, so that is not allowed to be described with any symmetry. So you can see why there's probably very, very little examples of ones that actually work to be symmetrical. Okay, so we're going to go through some examples of how you are able to check if they are. Okay, one, just by looking at the graphs, and then actually by doing some algebra. Okay, the algebra I like a little bit more because it actually allows you to see the exact answer. Okay, but here we're going to determine if the following are even, odd, or neither. So for these types of examples, especially that f at x equals x plus 1 over x, I would expect that you are going to use like Desmos to graph that to be able to tell me if it is even, odd, or neither symmetry. Okay, so for this example, you're going to check f at negative x equals negative f at x, and this is what the graph on Desmos would give you if you graphed x plus 1 over x. So you can see if this is negative 1, 2 here, it is positive 2 here, so you have the opposite there, so that it is going to be rotational, so it is a odd degree function. Okay, this one here, you're checking if f at x equals f at negative x. It is the same on either side, so it is an even degree. Okay, and then if you are to check this one, you can check both of them. Both of them do not work because you do not have any symmetry about your origin or your y-axis. So this one is neither. Okay, so that one's kind of more so just like looking at your at the graph and saying, oh, has this rotated about the origin? Oh, yep, so it is an odd degree. This one is symmetric about your y-axis, so it is an even degree. And then this one is not been rotated about the origin or is not symmetric on your y-axis, so it can't be either. Okay, so this one you had to check if it was even, if it was odd, but both of them don't work, so it's going to be neither. Okay, again, this might look a little confusing with the graph, so and what I'm going to show you is the algebra way, which is much nicer and makes a little bit more sense. Okay, so I would copy out this example, and it wants you to do without graphing. We're going to determine if each polynomial function has line symmetry about the y-axis, point symmetry about the origin, or neither. So if it's odd or even. Okay. So what we're going to do here is to figure out if it is line symmetry about the y-axis. That is when you have to check if because it is an even function, right? Even function with that 4. We're going to see if it has a line symmetry about the y-axis because that even function goes with the y-axis. Okay, so x to the 4 minus x squared plus 2. Remember, what you're going to check is f of x equal to f at negative x. So you're going to check, is this the same thing? Okay, so all you're going to do, remember, all you're going to do is see if the negative value of x is equal to the same value of x. So if you take your equation, f at x, what is f at x? You're going to go x4 minus x squared plus 2, but I want you to not have x in there anymore. I want you to have negative x. So this is actually going back to grade 11. Okay, if I want you to find negative x, you replace each of the x's in your regular equation with negative x. So this x to the 4 becomes negative x to the 4. This x squared becomes negative x squared. And then 2 doesn't have an x, so you just leave it as 2. When you solve that, negative x to the exponent 4 is x to the exponent 4. Subtract negative x squared. Negative x squared is x squared. So it's going to be subtract x squared plus 2. Well, when you solve that, does this, which is f of x, is that the same as your original function? Yes. So therefore you can conclude, that f at negative x equals f at x. Okay, so you would write therefore f at negative x is equal to f at x, and therefore x to the 4 minus x squared plus 2 has line symmetry about the y-axis. Yay! Okay, so that's how you're going to check. Again, I'm going to go through lots of examples here to help you check that, okay, or understand that. So again, another without graphing, we're going to determine if the polynomial function has line symmetry about the y-axis, point symmetry about the origin, or neither. So for B, we just did A. So for B, because it is odd degree, right, the 3 makes it an odd function, okay? We want to see if it has point symmetry about the origin. Our rule for point symmetry about the origin was our f at negative x, is that equal to the negative f at x? So that this is your odd degree rule here. So you're going to plug that in. So we want f at negative x to equal negative f at x. So plug in the negative x's to start with your function. So you have x cubed plus 3x. So you're going to go negative x cubed plus 3 times negative x. Remember, you're plugging in a negative x where you see x in those in that original equation. Okay. Simplify that. You get negative x cubed. Remember, a negative cubed is going to still be a negative. 3 times negative x is negative 3x. okay? If you were to pull out the negative sign, it becomes x cubed plus 3x, which is negative. This is f at x here, right? This is f at x here, and then so you have negative f at x, which is exactly what you want. So therefore, you have f at negative x equals negative f at x, and the function f at x equals x cubed plus 3x has point symmetry about the origin. Okay, so if you were doing this and it didn't equal the same thing, then no, it wouldn't have that symmetry. Okay, so one more example that I will show you is going to be C here. So we're going to look at this one on this slide. Is C here. So I want to know line symmetry about the y-axis, point symmetry about the origin, or neither. Okay. So since it is x cubed plus 2x squared minus 3, we know that it is a cubic function. Okay. So it may be odd and have point symmetry about the origin. So because you see the 3, it would be odd and have point symmetry about the origin. So we're going to figure that out. So remember, you're finding if f at negative x is equal to negative f at x. Okay, so f at negative x is equal to negative f at x is what you want to find. So again, remember, plug in negative x's for all of the x's you see in your original equation. When you simplify that, you should get negative x cubed plus 2x squared minus 3. Okay, but this is not going to be negative f at x, right? If you were to pull out a negative here, this would be f at x. Nope, it is not. Okay, f at x is plus x squared and net minus 3, so this one does not work. Okay, if you have negative f at x to equal negative x squared plus 2x squared minus 3, negative x cubed minus 2x squared plus 3, okay? And then because these two are not equal, then you know that you do not have, oops, sorry, did not realize that came down there, okay? Since they are not equal, then the function is not odd and does not have a point about the symmetry. So that there's an example of one that does not work. Okay, so you found f at negative x, and then you found negative f at x. Okay, these do not equal each other. They have, like, they almost do, but because they have negative here, but then this is positive, this one's negative, this one's negative, this one's positive, they are not equal. Okay, so you would say it is not odd and does not have a point symmetry about the origin. Okay, so that is how you do that algebraically, and you're going to get lots of practice in your homework doing that. Okay, so if you want to start your homework now, that is awesome. Just let me know if you have any questions. Good luck.